Hello everyone, and thank you for attending this presentation. My name is Adam Isa. I'll be presenting our work on electromigration checking using a stochastic effective current model. A short bio about myself. I have received my bachelor in computer and communications engineering from the American University of Beirut. I then joined Professor Najim's research group at the University of Toronto for a master's degree, and I'm currently working as an OR developer at IBS Software in Montreal, Canada. In this presentation, I'll begin by introducing what electromigration is, or EM, as an overview. I'll describe the traditional approach for EM checking. I'll also describe the stress-based EM simulation, which is a new approach. And I'll describe the effective current problem, which is the problem this paper addresses. We propose the stochastic effective current model as a solution, which we propagate to stochastic stress analysis, where we provide our novel approach for variance computation, and we'll end with a summary of the contributions. A power grid is a metallic mesh structure that delivers power from the outside package through the C4 bumps to the underlying logic circuit. It is a multi-layered structure where layers are interconnected using vias, and each layer is made up of one or more interconnect trees, which are structures of which we show a schematic on this slide. It is a connection of branches and junctions. For our context, since EM is a long-term failure mechanism, all short-term variations induced by capacitive or inductive elements are irrelevant. This is why we use the DC model of the power grid, which is simply a resistive mesh, where the logic circuit loading the grid is modeled as ideal current sources. The role of the power grid is to deliver acceptable voltage drops at all nodes, especially port nodes. The vector of voltage drops is given by G inverse I, where I is the vector of currents in the power grid and G is the conductance matrix. As for EM, it is defined as the mass transport of metal atoms due to the strong flow of electrons in the metal branches. So roughly speaking, the strong flow of electrons pushes metal atoms away in the direction of electron flow over the period of years of operation. This creates tensile and compressive stress inside the branches of the power grid. And when the tensile stress reaches some critical threshold, usually at a junction or a via, a void will eventually nucleate or occur, which is an area that is completely depleted of metal atoms. In this example, it leaves little room for current to flow in the barrier metal liner, which is conductive but of much higher resistance. This is how voids degrade the conductivity of the power grid until it eventually can no longer deliver acceptable voltage levels, and eventually the grid fails and the chip fails. In more severe cases, the void can completely disconnect the via or the junction, leading to an open circuit and hence an early failure of the chip. The traditional approach for EM checking has been to use Black's model, which dates back to 1969. It is an empirical model that relates the mean time to failure, or MTF, of an isolated branch to the density J of the current flowing inside that branch. The terms A, EA, and the exponent N are determined experimentally under accelerated testing conditions. The second component of the traditional approach is the use of the Black effect. The Black effect deems some branches to be immortal in case the product of their length with the density of the current flowing in them happens to meet some upper bound. Finally, the series model for grid failure is adopted, which means that the grid is assumed to have failed in case any of its branches fail. This approach has many shortcomings. First of all, the branch-by-branch manner of analyzing the grid ignores material flow between two connected branches, which is inaccurate. Also, it has been pointed out in the literature that fitting parameters in Black's model are invalid under normal operating conditions. Moreover, the Black effect might lead to optimistic results in case the branches happen to be short enough. On the other hand, the series model might lead to pessimistic results. In fact, the grid can survive multiple branch failures. Emerging solutions are stress-based, which means that they rely on tracking the stress evolution inside the metal branches of the power grid, as opposed to the empirical approach. They are based on a physical model called Korhonen's model, which is essentially a heat equation that is discretized in space. For every interconnect tree, it gives rise to an LTI system of the form S dot equals AS plus BU. The vector S holds the stress values at discretized nodes in the tree, and in particular at junctions in the tree, which is where voids usually happen. Junctions will be the states of interest in our work. However, when trying to simulate such a system over years of operation, we are immediately faced with the problem of what inputs U should we apply as stimulus to the system. The vector U holds the values of the current sources loading the grid. Since typical operation over a period of years is impossible to get, the common method has been to use DC currents as an effective current model. This is also motivated by the fact that EM has extremely slow dynamics, and so the LTI system will filter out any variations and only the DC component would be relevant. However, upon closer inspection of a simple single input, single output case, defining an effective current that leads to the same stress profile as the real current waveform would leads us to the conclusion that the effective current is actually a function of time. It is a function of the time over which we would like to obtain the response. So it is not truly DC, nor it can be simply a single number. A current metric must capture the variability. For example, we show on the left plot in red a low frequency pulsed current waveform with its noisy version shown in blue. The period of the pulses is 1 year. On the right-hand side, we show how the stress profile responds significantly to the pulses, but shows no sensitivity at all to the high frequency noise around the pulses. Simply using a DC current as effective current would mask significant variations, and it in fact leads to optimistic lifetime estimates of the grid. Our goal is to capture the variations in the stress profile by a variance band around some mean stress response. And the key to capture low frequency components is to consider modes of operation. By modes of operation, we mean the typical ones like high performance, long battery life, standby mode, or power down. And when large blocks in the chip switch between multiple modes of operation, they produce low frequency components. So in other words, our goal is to incorporate information about block operation to come up with a new effective current metric in an easy to use mechanism for users and propagate it to stress variance bands. More formally, let Ik of t represent the current drawn by block K. For our purposes, Ik of t will be a stochastic process. For every block K, in each mode, the user specifies the average power dissipation, which is in fact the design spec, and second, the average time spent or sojourn time in each mode. Now with this in hand, we can determine for every mode J, the average current mu Kj, which is deduced from the first specification by knowing the nominal voltage VDD. And second, we determine the probability that block K is in mode J at any given time. Probability is denoted by pkj, and it is simply the ratio of the time spent in mode J relative to the sum of all sojourn times for block K, which is denoted by tau K. As a consequence, we can determine Ik of these stochastic properties using a continuous time Markov chain model. The Markov model takes as input the user specifications and gives as output first the mean of the overall process IK, which is simply a weighted average of the mode currents, where the weights are the mode probabilities. Second, it gives an estimate of the variance of the process IK, which is given by the second equation on the right-hand side. Notice that we have used the term sigma squared Kj. This is an estimate of the variance within each mode. If it exists, the model accounts for it. However, since it is hard for users to provide that estimate, it can be safely set to 0 and leads to the approximation given by the equation that follows. And finally, the Markov model can determine the correlation coefficient of the process IK. We will make great use of this function when we deal with the general case, as we'll see later. As an example, we show a sample current waveform that is switching between 3 modes of operation. For each mode, we determine the average current and the average occupancy time, resulting in probabilities of each mode. And on the right-hand side, we see the mean current and the 2 standard deviations plot that we derive from the Markov model, that we get as an output of the Markov model. Moreover, we show in this example the estimate sigma over mu shown in the last column. We show how it increases as we make the mode currents and occupancy times farther away from each other. This adds to the variability of the process IK, which is reflected by higher values of sigma over mu. At this point, the problem is formulated as, given an LTI system whose inputs have known statistics, what can we say about the statistics of the system states? Now, this is a generic LTI problem that has 2 components. First one is determining the mean response. Second is determining the stress of the variance of the response. Now, by linearity, we know that applying mean inputs would provide the mean outputs. And this has been studied before in the literature by the work of Chatterjee et al. And our work is concerned with computing the variance of the system states. The solution for the LTI system is given by S of t equals e to the at S0, where S0 is the vector of initial stress values in the system. It is a vector of random variables, plus the convolution integral. Now, the first and second terms are uncorrelated, which means that the covariance matrix of the vector S is simply the sum of the covariance matrices of the first and the second terms. VAT, the first term, is the contribution of the initial state to the covariance matrix, and the second term is the contribution of the inputs. So superposition applies, which is exactly what we do on the next slide to compute the contribution of the initial state. We set the inputs to 0. And since we're interested in the variance of junctions, states of interest, then let Si be a state of interest. This variance of state Si is given by P transpose Vs0 P. Vs0 is the covariance matrix of the initial state vector S0. And more importantly, P is the output of an ODE given by P dot equals A transpose P. A is the system matrix. So we can compute the contribution of the initial state by simulating an ODE in time. As for the contribution of the inputs, we set the initial state to 0 by superposition, and we'll benefit from a special case where we consider the process Ik of t to be a zero mean white noise process whose intensity or variance is the one set by the Markov model we saw earlier. It follows that the variance of state Si due to the contribution of white noise inputs is given by P transpose QP, where Q is some predefined matrix. And the vector P is the output of the same ODE we saw on the last slide. As a result, we combine those 2 contributions in a single algorithm that gives the total variance computation under white noise input. On the right-hand side, we see the mean stress curve shown in blue with a 6 sigma variance band around it shown in red and the green curves. This algorithm is fast on individual trees. Table 1 reports on the CPU time for individual trees and the percentage drop in time to first nucleation, which can be as high as 80%. The last two rows in this table correspond to the largest single trees we could find in our benchmarks. The CPU time for the mean and variance is up to 25 minutes. The more interesting results are the full grid simulations that includes mean and variance. We set the input sigma over mu to be in the range of 20% to 33%. And we can see the impact on the MTF estimates, the percentage drop in MTF using the variance as opposed to only the DC approach can be as high as 50% drop. The total CPU time is still realistic of up to 8 hours for the largest benchmark in this example. So at this point, we have handled the special case when the inputs are white noise processes. Now we would like to handle correlated inputs. For that, we use an idea from communication systems, which is to use a shaping filter. A shaping filter is a system that takes a white noise process as input, whose autocorrelation function is an impulse at the origin, and produce at the output a process whose autocorrelation function is the one desired. By design, we design the shaping filter to have the autocorrelation at the output approximate the one generated by the Markov model. Each shaping filter in turn can be represented as an LTI system, and as a consequence, we end up with an augmented system for every tree that we simulate, but whose inputs are again white noise processes. This allows us to regain all the previous treatment for the white noise case. The augmented states can be in the thousands or sometimes hundreds of thousands, which makes this approach more computationally expensive. On the last table here, we show how it behaves on small to medium-sized systems. On a 3K node system, for example, the CPU time for mean and variance computations are about 5 minutes, and with a significant drop in time to first nucleation. To summarize, we have addressed the optimism induced by using DC inputs alone as effective currents. We've proposed a stochastic Markov model as a new effective current model. In an easy-to-use mechanism for users, we have also developed a novel approach for variance computation, where variance is the output of a numerically simulated ODE. We have also handled the general case of correlated inputs, and we've showed the impacts on MTF estimates, showing the importance of accounting for variance in EM simulation. Thank you all for listening, and I'll be happy to answer any of your questions.